Welcome to Coding in Data Science. I'm Bart Poulsen, and what we're going to do in this series of videos is we're going to take a little look at the tools of data science. So I'm inviting you to know your tools, but probably even more important than that is to know their proper place. Now, I mention that because a lot of the times when people talk about data tools, they talk about it as though that were the same thing as data science, as though they were the same set. But I think if you look at it for just a second, that's not really the case. Data tools are simply one element of data science, because data science is made up of a lot more than the tools that you use. It includes things like business knowledge. It includes the meaning making and interpretation. It includes social factors. And so there's much more than just the tools involved. That being said, you will need at least a few tools. And so we're going to talk about some of the things that you can use in data science if it works well for you. In terms of getting started, the basic things, number one is spreadsheets. It's the universal data tool, and I'll talk about how they play an important role in data science. Number two is a visualization program called Tableau. There's Tableau Public, which is free, and there's Tableau Desktop, and there's also something called Tableau Server. But Tableau is a fabulous program for data visualization, and I'm convinced for most people provides the great majority of what they need. And though, while it's not a tool, I do need to talk about the formats used in web data because you have to be able to navigate that when doing a lot of data science work. Then we can talk about some of the essential tools for data science. Those include the programming language R, which is specifically for data. There's the general purpose programming language Python, which has been well adapted to data. And there's the database language SQL, or SQL for a structured query language. Then if you want to go beyond that, there are some other things that you can do. There are the general purpose programming languages C, C++, and Java, which are very frequently used to form the foundation of data science, and sort of high-level production code is going to rely on those as well. There's the command line interface language, Bash, which is very common as a very quick tool for manipulating data. And then there's the sort of wildcard, supercharged regular expressions, or regex. We'll talk about all of these in separate courses. But as you consider all the tools that you can use, don't forget the 80-20 rule, also known as the Pareto principle. And the idea here is that you're going to get a lot of bang for your buck out of a small number of things. And I'm going to show you a little sample graph here. Imagine that you have 10 different tools, and we'll call them A through B. A does a lot for you, B does a little bit less, and it kind of tapers down to you've got a bunch of tools that do just a little bit of stuff that you need. Now, instead of looking at the individual effectiveness, look at the cumulative effectiveness. How much are you able to accomplish with a combination of tools? Well, the first one's right here at 60% where the tool started. Then you add on the 20% from B and it goes up, and then you add on C and D, and you add up little smaller pieces. And by the time you get to the end, you've got 100% of effectiveness from your 10 tools combined. The important thing about this is you only have to go to the second tool. That's 2 out of 10. So that's B, that's 20% of your tools. And in this made up example, you've got 80% of your output. So 80% of the output from 20% of the tools. That's a fictional example of the Pareto principle, but I find in real life it tends to work something approximately like that. And so you don't necessarily have to learn everything, and you don't have to learn how to do everything in everything. Instead, you want to focus on the tools that will be most productive, and specifically most productive for you. So in sum, let's say these three things. Number one, coding, or simply the ability to manipulate data with programs and computers. Coding is important, but data science is much greater than the collection of tools that's used in it. And then finally, as you're trying to decide what tools to use and what you need to learn and how to work, remember the 80-20 rule. You're going to get a lot of bang from a small set of tools. So focus on the things that are going to be most useful for you in conducting your own data science projects. As we begin our discussion of coding and data science, I actually want to begin with something that's not coding. I want to talk about applications, or programs that are already created that allow you to manipulate data. And we're going to begin with the most basic of these spreadsheets. We're going to do the rows and columns and cells of Excel. And the reason for this is you need spreadsheets. Now, you may be saying to yourself, no, not me. Because you know what? I'm fancy. I'm working in my big set of servers. I got fancy things going on. But you know what? You too, fancy people, you need spreadsheets as well. And there's a few reasons for this. Most importantly, spreadsheets can be the right tool for data science in a lot of circumstances. There are a few reasons for that. Number one, spreadsheets, they're everywhere. They're ubiquitous. They're installed on 1 billion machines around the world. And everybody uses them. They probably have more data sets in spreadsheets than anything else. And so it's a very common format. Importantly, it's probably your client's format. A lot of your clients are going to be using spreadsheets for their own data. I've worked with billion-dollar companies that keep all of their data in spreadsheets. And so when you're working with them, you need to know how to manipulate that and how to work with it. Also, regardless of what you're doing, spreadsheets, or specifically CSV, comma-separated value files, are sort of the lingua franca, the universal interchange format for data transfer to allow you to take it from one program to another. And then, truthfully, in a lot of situations, they're really easy to use. And if you want a second opinion on this, let's take a look at this ranking that is a survey of data mining experts. It's the KD Nuggets data mining poll. And these are the tools they most use in their own work. And look at this. Lowly Excel is 5th on the list. And in fact, what's interesting about it, it's above Hadoop and Spark, two of the major big data fancy tools. And so Excel really does have a place of pride in a toolkit for a data analyst. Now, since we're going to sort of the low-tech end of things, let's talk about some of the things that you can do with a spreadsheet. Number one, they're really good for data browsing. You actually get to see all of the data in front of you, which isn't true if you're doing something like R or Python. They're really good for sorting data. Sort by this column, then this column, then this column. They're really good for rearranging columns and cells and moving things around. They're good for finding and replacing and seeing what happened so you know that it worked right. Some more uses. They're really good for formatting, especially conditional formatting. They're good for transposing data, switching the rows and the columns. They make that really easy. They're good for tracking changes. Now, it's true if you're a big fancy data scientist, you're probably using GitHub. But for everybody else in the world, spreadsheets and the tracking changes is a wonderful way to do it. You can make pivot tables. That allows you to explore the data in a very hands-on way, in a very intuitive way. And they're also really good for arranging the output for consumption. Now, when you're working with spreadsheets, however, there's one thing you need to be aware of. They're really flexible, but that flexibility can be a problem, and that when you're working in data science, you specifically want to be concerned about something called tidy data. That's a term I borrowed from Hadley Wickham, very well-known developer in the R world. Tidy data is for transferring data and making it work well. There's a few rules here that undo some of the flexibility inherent in spreadsheets. Number one, what you want to do is have a column be equivalent to the same thing as a variable. Columns, variables, they are the same thing. And then rows are exactly the same thing as cases. And that you have one sheet per file, and that you have one level of measurement, say individual, then organization, then state, per file. Again, this is undoing some of the flexibility that's inherent in spreadsheets, but it makes it really easy to move the data from one program to another. Let me show you how all this works. You can try this in Excel. If you've downloaded the files for this course, we simply want to open up this spreadsheet. Let me go to Excel and show you how it works. So when you open up the spreadsheet, what you get is totally fictional data here that I made up, but it's showing sales over time of several products at 2 locations, like if you're selling stuff at a baseball field. And this is the way spreadsheets often appear. We got blank rows and columns. We got stuff arranged in a way that makes it easy for the person to process it. And we got totals here and with formulas, putting them all together. And that's fine. That works well for the person who made it. And then that's for 1 month. And then we have another month right here. And then we have another month right here. And then we combine them all for the first quarter of 2014. We've got some headers here. We've got some conditional formatting and changes. And if we come to the bottom, we've got a very busy line graphic that eventually loads. It's not a good graphic, by the way, but similar to what you will often find. So this is the stuff that, while it may be useful for the client's own personal use, you can't feed this into R or Python. It'll just choke and it won't know what to do with it. And so you need to go through a process of tidying up the data. And what this involves is undoing some of this stuff. So for instance, here's data that is almost tidy. Here we have a single column for the date, a single column for the day, a column for the site. So we have two locations, A and B. And then we have 6 columns for the 6 different things that are sold and how many were sold on each day. Now, in certain situations, you would want the data laid out exactly like this. If you're doing, for instance, a time series, you'll do something vaguely similar to this. But for true tidy stuff, we're going to collapse it even further. Let me come here to the tidy data. And now what I've done is I've created a new column that says, what is the item being sold? And so, by the way, what this means is that we've got a really long data set now. It's got over 1,000 rows. Come back up to the top here. But what that shows you is that now it's in a format that's really easy to import from one program to another. That makes it tidy, and you can remanipulate it however you want once you get to each of those. So let's sum up our little presentation here in a few lines. Number one, no matter who you are, no matter what you're doing in data science, you need spreadsheets. And the reason for that is that spreadsheets are often the right tool for data science. Keep one thing in mind though, and that is as you're moving back and forth from one language to another, tidy data or well-formatted data is going to be important for exporting data into your analytical programmer language of choice. As we move through coding and data science, and specifically the applications that can be used, there's one that stands out for me more than almost anything else, and that's Tableau and Tableau Public. Now, if you're not familiar with these are visualization programs. The idea here is that when you have data, the most important thing you can do is to first look and see what you have and work with it from there. And in fact, I'm convinced that for many organizations, Tableau might be all that they really need. It will give them the level of insight that they need to work constructively with data. So let's take a quick look by going to tableau.com. Now there are a few different versions of Tableau. Right here we have Tableau Desktop and Tableau Server, and these are the paid versions of Tableau. They actually cost a lot of money, unless you work for a nonprofit organization, in which case you can get them for free, which is a beautiful thing. What we're usually looking for, however, is not this paid version, but we're looking for something called Tableau Public. And if you come in here and go to products, and we've got these 3 paid ones, come over here to Tableau Public. And we click on that, it brings us to this page. It's public.tableau.com. And this is the one that has what we want. It's a free version of Tableau with one major caveat. You don't save files locally to your computer, which is why I didn't give you a file to open. Instead, it saves them to the web in a public form. So if you're willing to trade privacy, you can get an immensely powerful application for data visualization. That's a catch for a lot of people, which is why people are willing to pay a lot of money for the desktop version. And again, if you work for a nonprofit, you can get the desktop version for free. But I'm going to show you how things work in Tableau Public. So that's something that you can work with personally. The first thing you want to do is you want to download it. And so you put in your email address, you download, it's going to know what you're on. It's a pretty big download. And once it's downloaded, you can install it and open up the application. And here I am in Tableau Public right here. This is the blank version. By the way, you also need to create an account with Tableau in order to save your stuff online and to see it. We'll show you what that looks like. But you're presented with a blank thing right here. And the first thing you need to do is you need to bring in some data. I'm going to bring in an Excel file. Now, if you've downloaded the files for the course, you'll see that there's this one right here, DSO322 Tableau Public .xlsx. It's a Excel file. And in fact, it's the one that I used in talking about spreadsheets in the first video in this course. I'm going to select that one and I'm going to open it. And a lot of programs don't like bringing in Excel because it's got all the worksheets and all the weirdness in it. This one works better with it. But what I'm going to do is I'm going to take the tidy data. By the way, you see that it put them in alphabetical order here. And I'm going to take tiny data. I'm just going to drag it over to let it know that it's the one that I want. And now what it does is it shows me a version of the data set along with things that you can do here. You can rename it. You can create bin groups. There's a lot of things that you can do here. I'm going to do something very, very quick with this particular one. Now I've got the data set right here. What I'm going to do now is I'm going to go to a worksheet. That's where you actually create stuff. I'll cancel that and go to worksheet 1. Okay. This is a drag and drop interface. And so what we're going to do is we're going to pull the bits and pieces of information we want to make graphics. There's immense flexibility here. I'm going to show you two very basic ones. I'm going to look at the sales of my fictional ballpark items. So I'm going to grab sales right here. And I'm going to put that as the field that we're going to measure. Okay, and you see it put it down right here. And this is our total sales. We're going to break it down by item and by time. So let me take item right here. And you can drag it over here, or I can put it right up here into rows. Those will be my rows, and that's how many we've sold total of each of the items. Fine, that's really easy. And then let's take date, and we'll put that here in columns to spread it across. Now, by default, it's doing it by year. I don't want to do that. I only have 3 months of data. And so what I can do is I can click right here, and I can choose a different time frame. I can go to quarter, but that's not going to help because I only have 1 quarter's worth of data. That's 3 months. I'm going to come down to week. Actually, let me go to day. If I do day, you see it gets enormously complicated, so that's no good. So I'm going to back up to week. And I've got a lot of numbers there, but what I want is a graph. And so to get that, I'm going to come over here and click on this and tell it that I want a graph. And so we're seeing the information, except it lost item. So I'm going to bring item and I'm going to put it back up into this graph to say this is a row for the data. And now I've got rows for sales by week for each of my items. That's great. I want to break it down one more by putting in the site, the place that it's sold. And so I'm going to grab that and I'm going to put it right over here. And now you see I've got it broken down by the item that is sold and the different sites. And I'm going to color the sites. And all I got to do to that is I'm going to grab site and drag it onto color. Now I've got 2 different colors for my sites. And this makes it a lot easier to tell what's going on. And in fact, there's some other cool stuff you can do. One of the things I'm going to do is I can come over here to analytics and I can tell it, for instance, to put an average line through everything. So I'll just drag this over here and say, now we have the average for each line. That's good. And I can even do forecasting. Let me get a little bit of a forecast right here. I'll drag this on. And if you go over here, I can get this out of the way for a second. Now I have a forecast for the next few weeks. And that's a really convenient, quick and easy thing. And again, for some organizations, that might be all that they really need. And so what I'm showing you here is the absolute basic operation of Tableau, which allows you to do an incredible range of visualizations and manipulate the data and create interactive dashboards. There's so much to it, and we'll show that in another course. But for right now, I want to show you one last thing about Tableau Public, and that is saving the files. So now when I come here and save it, it's going to ask me to sign into Tableau Public. Now I sign in, and it asks me how I want to save this. Same name as the video. There we go, and I'm going to hit save. And then that opens up a web browser. And since I'm already logged into my account, see, here's my account, my profile. Here's the page that I created. And it's got everything I need there. I'm going to edit just a few details. I'm going to say, for instance, I'm going to leave its name like that. I could put more of a description in there if I wanted. I can allow people to download the workbook and its data. I'm going to leave that there so you can download it if you need to. If I had more than one tab, I would do this thing that says show the different sheets as tabs. Hit save. And there's my data set. And also it's published online and people can now find it. And so what you have here is an incredible tool for creating interactive visualizations. You can create them with drop-down menus and you can rearrange things and you can make an entire dashboard. It's a fabulous way of presenting information. And as I said before, I think that for some organizations, this may be as much as they need to get really good, useful information out of their data. And so I strongly recommend that you take some time to explore with Tableau, either the paid desktop version or the public version, and see what you can do to get some really compelling and insightful visualizations out of your work in data science. For many people, their first experience of coding in data science is with the application SPSS. Now, I think of SPSS and the first thing that comes to my mind is sort of life in the ivory tower, though this looks more like, Harry Potter. But if you think about it, the package name SPSS comes from Statistical Package for the Social Sciences, although if you ask IBM about it now, they'll act like it doesn't stand for anything. But it has its background in social science research, which is generally academic, and truthfully, I'm a social psychologist, and that's where I first learned how to use SPSS. But let's take a quick look at their webpage, ibm.com/SPSS. If you type that in, that'll just be a alias that'll take you to IBM's main webpage. Now, IBM didn't create SPSS, but they bought it around version 16, and it was very briefly known as PASW, Predictive Analytics Software. That only lasted briefly, and now it's back to SPSS, which is where it's been for a long time. SPSS is a desktop program. It's pretty big. It does a lot of things. It's very powerful. It's used in a lot of academic research. It's also used in a lot of business consulting, management, and even some medical research. And the thing about SPSS is it looks like a spreadsheet, but it has drop-down menus to make your life a little bit easier compared to some of the programming languages that you can use. Now, you can get a free temporary version. If you're a student, you can get a cheap version. Otherwise, SPSS costs a lot of money. But if you have it one way or the other, when you open it up, this is what it's going to look like. I'm showing SPSS version 22. Now, it's currently on 24. And the thing about SPSS versioning is in any other software package, these would be point updates. So I sort of feel like we should be on 17.3 as opposed to 22 or 24, because the variations are so small that anything you learn from the earlier ones is going to work in the later ones. And there's a lot of backwards and forwards compatibility. So I'd almost say that this one, the version you have, practically doesn't matter. You get this little welcome splash screen, and if you don't want to see it anymore, you can get rid of it. I'm just going to hit cancel here. And this is our main interface. Looks a lot like a spreadsheet. The difference is you have a separate pane for looking at variable information, and then you have separate windows for output, and then an optional one for something called syntax. But let me show you how this works by first opening up a data set. SPSS has a lot of sample data sets in them, but they're not easy to get to, and they're really well hidden. On my Mac, for instance, let me go to where they are. In my Mac, I go to the Finder. I have to go Mac to Applications, to the folder IBM, to SPSS, to Statistics, to 22, the version number, to Samples. Then I have to say I want the ones that are in English, and then it brings them up. The .sav files are the actual data files. There are different kinds in here. So .sps is a different kind of file. And then we have a different one about planning analyses. So there are versions of it. I'm going to open up a file here called marketvalues.sav. It's a small data set in SPSS format. And if you don't have that, you can open up something else. It really doesn't matter for now. By the way, in case you haven't noticed, SPSS tends to be really, really slow when it opens. It also, despite being at version 24, tends to be kind of buggy and crashes. And so when you work with SPSS, you want to get in the habit of saving your work constantly. and also being patient when it's time to open the program. So here's a data set that just shows addresses and house values and square feet for some information. This, I don't even know if this is real information. It looks artificial to me. But SPSS lets you do point and click analyses, which is unusual for a lot of things. So I'm going to come up here and I'm going to say, for instance, make a graph. I'm actually going to use what's called a legacy dialog to get a histogram of house prices. So I simply click values, put that right there, and I'll put a normal curve on top of it and hit OK. And then it's going to open up a new window, and it opened up a microscopic version of it here. So I'm going to make that bigger. This is the output window. And so this is a separate window, and it has a navigation pane here on the side. It tells me where the data came from, and it saves the command here. And then, there's my default histogram. And so we see most of the houses were right around $125,000, and then they went up to at least 400,000. I have a mean of 256,000, a standard deviation of about 80,000, and there's 94 houses in the data set. Fine, that's great. The other thing I can do is if I want to do some analyses, let me go back to the data just for a moment. For instance, I can come here to analyze and I can do descriptives. I'm actually going to do, I'm going to do one here called explore. And I'll take the purchase price and I'll put it right here. And I'm going to get a whole bunch of stuff just by default. I'm going to hit OK. And it goes back to the output window. Once again, made it tiny. And so now you see beneath my chart, I now have a table and I've got a bunch of information, a stem and leaf plot, and I've got a box plot too. A great way of checking for outliers. And so this is a really convenient way to save things. You can export this information as images. You can export the entire file as an HTML. You can do it as a PDF or a PowerPoint. There's a lot of options here, and you can customize everything that's on here. Now, I just want to show you one more thing that makes your life so much easier in SPSS. You see right here that it's putting down these commands. It's actually saying graph and then histogram normal equals value. And then down here, we've got this little command right here. Most people don't know how to save their work in SPSS, and they kind of just have to do it over again every time. But there's a very simple way to do this. What I'm going to do is I'm going to open up something called a syntax file. I'm going to go to New, Syntax. And this is just a blank window that's a programming window. It's for saving code. And let me go back to my analysis I did a moment ago. I'll go back to Analyze. I can still get at it right here. And Descriptives and Explore. And my information is still there. And what happens here is even though I set it up with drop-down menus and point and click, if I do this thing paste, then what it does is it takes the code that creates that command and it saves it to this syntax window. And this is just a text file. It saves it as .sps, but it's a text file that can be opened in anything. And what's beautiful about this is it's really easy to copy and paste. And you can even take this into like Word and do find and replace on it. And it's really easy to replicate the analyses. And so for me, SPSS is a good program, but until you use syntax, you don't know the true power of it, and it makes your life so much easier as a way of operating it. Anyhow, this is my extremely brief introduction to SPSS. All I want to say is that it's a very common program, kind of looks like a spreadsheet, but it gives you a lot more power and options, and you can use both drop-down menus and text-based syntax commands as well to automate your work and make it easier to replicate it in the future. I want to take a look at one more application for coding and data science that's called JASP. This is a new application, not very familiar to a lot of people and still in beta, but with amazing promise. You can basically think of it as a free version of SPSS. And you know what? We love free. But JASP is not just free, it's also open source, and it's intuitive, and it makes analyses replicable, and it even includes Bayesian approaches. And so take that all together, we're pretty happy and we're jumping for joy. So before we move on, you just may be asking yourself, JASP, what is that? Well, the creators emphatically deny that it stands for just another statistics program, but be that as it may, we'll just go ahead and call it JASP and use it very happily. You can get to it by going to jasp-stats.org, and let's take a look at that right now. JASP is a new program. They say a low-fat alternative to SPSS, but it is a really wonderful, great way of doing statistics. You're going to want to download it, specifying your platform. It even comes in Linux format, which is beautiful. And again, it's beta, so stay posted. Things are updating regularly. And if you're on Mac, you're going to need to use Xquartz, but that's an easy thing to install. It makes a lot of things work better. And it's a wonderful way to do analyses. When you open up JASP, it's going to look like this. It's a pretty blank interface, but it's really easy to get going with it. So for instance, you can come over here to File, and you can even choose some example data sets. So for instance, here's one called Big Five. That's personality factors. And you've got data here that's really easy to work with. Let me scroll this over here for a moment. So there's our 5 variables. And let's do some quick analyses with these. Say, for instance, we want to get descriptives. We can pick a few variables. Now, if you're familiar with SPSS, the layout feels very much the same, and the output looks a lot the same. You know, all I have to do is select what I want, and it immediately pops up over here. And then I can choose additional statistics. I can get quartiles. I can get the median. And you can choose plots. Let's get some plots. All I do is click on it and they show up. And that's a really beautiful thing. And you can modify these things a little bit. So for instance, I can take the plots and let's see if I can drag that down. And if I make it small enough, I can see the 5 plots. Well, I went a little too far on that one. Anyhow, you can do a lot of things here, and I can hide this. I can collapse that. And I can go on and do other analyses. Now, what's really neat, though, is when you navigate away from it. So I just clicked in the blank area of the results pane. We're back to the data here. But if I click on one of these tables, like this one right here, it immediately brings up the commands that produced it. And I can just modify it some more if I want. Say I want skewness and kurtosis. Boom, they're in there. It's an amazing thing. And then I can come back out here. I can click away from that. And I can come down to the plots, expand those, and if I click on that, it brings up the commands that made them. It's an amazingly easy and intuitive way to do things. Now, there's another really nice thing about JASP, and that is that you can share the information online really well through a program called osf.io. That stands for the Open Science Foundation. That's its web address, osf.io. So let's take a quick look at what that's like. Here's the Open Science Framework website, and it's a wonderful service. It's free, and it's designed to support open, transparent, accessible, accountable, collaborative research. And I really can't say enough nice things about it. What's neat about this is once you sign up for OSF, you can create your own area, and I've got one of my own. I'll go to that right now. So for instance, here's the Data Lab page in Open Science Framework. And what I've done is I created a version of this JASP analysis, and I've saved it here. In fact, let's open up my JASP analysis in JASP, and then I'll show you what it looks like in OSF. So let's first go back to JASP. And when we're here, we can come over to File and click Computer. And I just saved this file to the desktop. Click on Desktop. And you should have been able to download this with all the other files, DSO324JASP. I'm going to double click on that to open it. And now it's going to open up a new window. And you see I was working with the same data set, but I did a lot more analyses. I've got these graphs. I have correlation scatter plots. Come down here, I did a linear regression. And we just click on that and you can see the commands that produced it as well as the options. Didn't do anything special for that, but I did do some confidence intervals and specified that. And it's really a great way to work with all this. I'll click back in an empty area and you can see the commands go away. And so I've got my output here in JASP. When I saved it though, I had the option of saving it to OSF. In fact, if you go to this web page, osf.io/3t2jg, you'll actually be able to go to a page where you can see and download the analysis that I conducted. Let's take a look. This is that page. There's the address I just barely gave you. And what you see here is the same analysis that I conducted. It's all right here. So if you're collaborating with people, or if you want to show things to people, this is a wonderful way to do it. Everything's right there. Now this is a static image, but up at the top, people have the option of downloading the original file and working with it on their own. So in case you can't tell, I'm really enthusiastic about JASP and about its potential. Still in beta, still growing rapidly. I see it really as an open source, free, and collaborative replacement to SPSS. And I think it's going to make data science work so much easier for so many people. I strongly recommend you give JASP a close look. Let's finish up our discussion of coding and data science, the applications part of it, by just briefly looking at some other software choices. And I'll have to admit, it gets kind of overwhelming because there are just so many choices. Now, this is in addition to the spreadsheets and Tableau and SPSS and JASP that we've already talked about. I mean, there's so much more than that. I'm going to give you a range of things that I'm aware of, and I'm sure I've left out some important ones or things that other people like really well. But these are some common choices and some less common but interesting ones. Number one, in terms of things that I did not mention, is SAS. SAS is an extremely common analytical program, very powerful, used for a lot of things. It's actually the first program that I learned. And on the other hand, it can be kind of hard to use and it can be expensive. But there's a couple of interesting alternatives. SAS also has something called the SAS University Edition. If you're a student, this is free and it's slightly, reduced in what it does. But the fact that it's free, and also it runs in a virtual machine, which makes it an enormous download, but it's a good way to learn SAS if it's something that you want to do. SAS also makes a program that I really love were it not so extraordinarily expensive, and that is called JUMP. And it's a visualization software. Think a little bit of like Tableau, how we saw you work with it visually. And this one, you can drag things around. It's a really wonderful program. I personally find it prohibitively expensive. Another very common choice among working analysts is Stata, and some people use Minitab. Now for mathematical people, there's MATLAB, and then of course there's Mathematica itself, but that's really more a language than a program. On the other hand, Wolfram, who makes Mathematica, is also the people who give us Wolfram Alpha. Most people don't think of this as a stats application because you can run it on your iPhone. But Wolfram Alpha is in fact incredibly capable. And especially if you pay for the pro account, you can do amazing things in this, including analyses, regression models, visualizations. And so it's worth taking a little closer look at that also, because it actually provides a lot of the data that you need. So Wolfram Alpha is an interesting one. Now, several applications that are more specifically geared towards data mining. So you don't want to do your regular, little t-tests and stuff on these, but there's RapidMiner, and there's Nime and Orange. And those are all really nice to use because they are control languages where you drag nodes onto a screen and you connect them with lines and you can see how things run through. All three of them are free or have free versions, and all three of them work in pretty similar manners. There's also BigML, which is for machine learning. And this is unusual because it's browser based. It runs on their servers. There's a free version, although you can't download a whole lot. It doesn't cost a lot to use BigML, and actually is a very friendly, very accessible program. Then in terms of programs you can actually install for free on your own computer, there's one called SOFA Statistics. That means Statistics Open for All. Kind of a cheesy title, but it's a good program. And then one with a web page straight out of 1990 is PAST3. This is paleontological software. On the other hand, does do very general stuff. It runs on many platforms and it's a really powerful thing, and it's free, but it is relatively unknown. And then speaking of relatively unknown, one that's near and dear to my heart is a web application called StatCrunch. It costs, but it costs like $6 or $12 a year. It's really cheap, and it's very good, especially for basic statistics and for learning. I used it in some of the classes that I was teaching. And then if you're deeply wedded to Excel and you just can't stand to leave that environment, you can purchase add-ins like Excel Stat, which give you a lot of statistical functions within the Excel environment itself. That's a lot of choices. And the most important thing here is don't get overwhelmed. There's a lot of choices, but you don't even have to try all of them. Really, the important question is what works best for you and the projects that you're working on. There's a few things you might want to consider in that regard. First off is functionality. Does it actually do what you want, or does it even run on your machine? You don't need everything that a program can do. I mean, think about all the stuff that Excel can do. People probably use 5% of what is available. Then there's also ease of use. Some of these programs are a lot easier to use than the others. And I personally find that the ones that are easy to use, I like them. And so you might say, no, I need to program because I need to do custom stuff, but I'm willing to bet that 95% of what people do does not require anything custom. Also, the existence of a community. Constantly when you're working, you come across problems, don't know how to solve it, and being able to simply get online and do a search for an answer and have enough of a community that there are people there who have put answers up and discuss these things. Those are wonderful. Some of these programs have very substantial communities. Some of them it's practically non-existent, and you get to decide how important that is to you. And then finally, of course, there's the issue of cost. Many of these programs I mentioned are free. Some of them are very cheap. Some of them run on sort of a freemium model, and some of them are outrageously expensive. So you don't buy them unless somebody else is paying for it. So these are some of the things that you want to keep in mind when you're trying to look at various programs. Also, let's mention this. Don't forget the 80-20 rule. You're going to be able to do most of the stuff that you need to do with only a small number of tools. 1 or 2, maybe 3 will probably be all that you ever need. So you don't need to explore the range of every possible tool. Find something that does what you need, find something you're comfortable with, and really try to extract as much value as you can out of that. So in sum, in our discussion of available applications for coding and data science, first remember applications are tools. They don't drive you, you use them. And that your goals are what drive the choice of your applications and the way that you do it. And the single most important thing is to remember what works for you may work well for somebody else. If you're not comfortable with it, if it's not the questions you address, then it's more important to think about what works for you and the projects that you're working on as you make your own choices for tools for working in data science. When you're coding in data science, one of the most important things you can do is be able to work with web data. And if you work with web data, you're going to be working with HTML. Now, in case you're not familiar with it, HTML is what makes the World Wide Web go round. What it stands for is Hypertext Markup Language. And if you've never dealt with web pages before, here's a little secret. Web pages are just text. It's just a text document, but it uses tags to define the structure of the document, and a web browser knows what those tags are and it displays them in the right way. So for instance, some of the tags, they look like this. They're in angle brackets, and you have angle bracket and then a beginning tag, so body. Then you have the body, the main part of your text, and then you have in angle brackets and a backslash body to let the computer know that you're done with that part. You also have P and backslash P for paragraphs. H1 is for header 1, and you put it in between that text. TD is for table data, or the cell in a table, and you mark it off that way. If you want to see what it looks like, just go to this document, DSO331HTML.text. I'm going to go to that one right now. Now, depending on what text editor you open this up, it may actually give you the web preview. I've opened it up in TextMate, and so it actually is showing the text the way I typed it. I typed this manually, I just typed it all in there, and I have HTML to say what a document is. I have an empty header, but that sort of needs to be there. This I say what the body is, and then I have some text. LI is for list items. I have headers. This is for a link to a web page. Then I have a small table. And if you want to see what this looks like when it's actually displayed as a web page, we'll just go up here to Window and Show Web Preview. This is the same document, but now it's in a browser. And that's how you make a web page. Now, I know this is very fundamental stuff, but the reason this is important is because if you're going to be extracting data from the web, you have to understand how that information is encoded in the web and is going to be in HTML most of the time for a regular web page. Now, I will mention something that there's another thing called CSS, and web pages use CSS to define the appearance of a document. HTML is theoretically there to give the content, and CSS gives the appearance, and that stands for Cascading Style Sheets. I'm not going to worry about that right now because we're really interested in the content. And now you have the key to being able to read web pages and pull data from web pages for your data science projects. So in sum, first, the web runs on HTML. That's what makes the web pages that are there. HTML defines the page structure and the content that's in the page. And you need to learn how to navigate the tags and the structure in order to get data from the web pages for your data science projects. The next step in coding in data science when you're working with web data is to understand a little bit about XML. I like to think of this as the part of web data that follows the imperative, data define thyself. XML stands for Extensible Markup Language. And what it is, XML is semi-structured data. What that means is that tags define data so a computer knows what a particular piece of information is. But unlike HTML, the tags are free to be defined any way you want. And so you have this enormous flexibility in there, but you're still able to specify it so the computer can read it. Now, there's a couple of places where you're going to see XML files. Number one is in web data. HTML defines the structure of a web page, but if they're feeding data into it, then that will often come in the form of an XML file. Interestingly, Microsoft Office files, if you have docx or XLSX, X part at the end stands for a version of XML that's used to create these documents. If you use iTunes, the library information that has all of your artists and your genres and your ratings and stuff, that's all stored in an XML file. And then finally, data files that often go with particular programs can be saved as XML as a way of representing the structure of the data to the program. And for XML, tags use opening and closing angle brackets just like HTML did. Again, the major difference is that you're free to define the tags however you want. So for instance, thinking about iTunes, you can define a tag that's genre, and you have the angle brackets and genre to begin that information. And then you have the angle brackets with the backslash to let it know you're done with that piece of information. Or you can do it for composer, or you can do it for rating, or you can do it for comments. And you can create any tags you want, and you put the information in between those two things. Now, let's take an example of how this works. I'm going to show you a quick data set that comes from the web. It's at ergast.com and API. This is a website that stores information about automobile Formula One racing. Let's go to this webpage and take a quick look at what it's like. So here we are at ergast.com, and it's the API for Formula One. And what I'm bringing up is the results of the 1957 season in Formula One racing. And here you can see who the competitors were in each race and how they finished and so on. So this is a data set that's being displayed in a web page. If you want to see what it looks like in XML, all you have to do is type XML onto the end of this .xml. I've done that already, so I'm just going to go to that one. You see, it's only this little bit that I've added .xml. Now it looks exactly the same because the web page is structuring XML data by default. But if you want to see what it looks like in its raw format, just do an option click on the web page and go to View Page Source. At least that's how it works in Chrome. And this is the structured XML page. And you can see we've got tags here. It says race name, circuit name, location. And obviously these are not standard HTML tags. They're defined for the purposes of this particular data set. But we begin with one, we have circuit name right there, and then we close it using the backslash right there. And so this is structured data. The computer knows how to read it, which is this is how it displays it by default. And so it's a really good way of displaying data, and it's a good way to know how to pull data from the web. You can actually use what's called an API, an application programming interface, to access this XML data, and it pulls it in along with its structure, which makes working with it really easy. What's even more interesting is how easy it is to take XML data and convert it between different formats because it's structured and the computer knows what you're dealing with. So for example 1, it's really easy to convert XML to CSV or comma separated value files. That's the spreadsheet format because it knows exactly what the headings are and what piece of information goes in each column. Example 2, it's really easy to convert HTML documents to XML because you can think of HTML with its restricted set of tags as sort of a subset of the much freer XML. And 3, you can convert CSV or your spreadsheet comma separated value to XML and vice versa. You can bounce them all back and forth because the structure is made clear to the programs that you're working with. So in sum, here's what we can say. Number 1, XML is semi-structured data. What that means is it has tags to tell the computer what the piece of information is, but you can make the tags whatever you want them to be. And XML is very common for web data, and it's really easy to translate the formats XML, HTML, CSV, so on and so forth. It's really easy to translate them back and forth, which gives you a lot of flexibility in manipulating data so you can get into the format you need for your own analysis. The last thing I want to mention about coding in data science and web data is something called JSON. And I like to think of it as a version of smaller is better. Now, what JSON stands for is JavaScript Object Notation, although JavaScript is supposed to be one word. And what it is that like XML, JSON is semi-structured data. That is, you have tags that define the data so the computer knows what each piece of information is. But like XML, the tags can vary freely. And so there's a lot in common between XML and JSON. So XML is a markup language. That's what the ML stands for. And that gives meaning to the text. It lets the computer know what each piece of information is. Also, XML allows you to make comments in the document, and it allows you to put metadata in the tags. You can actually put some information there in the angle brackets to provide additional context. JSON, on the other hand, is specifically designed for data interchange. And so it's got that special focus. And the structured JSON corresponds with data structures. It directly represents objects and arrays and numbers and strings and booleans. And that works really well with the programs that you use to analyze data. Also, JSON is typically shorter than XML because it does not require the closing tags. Now, there are ways to do that with XML, but that's not typically how it's done. As a result of these differences, JSON is basically taking XML's place in web data. XML still exists, still used for a lot of things, but JSON is slowly replacing it. And we'll take a look at the comparison between the three by going back to the example we used in XML. This is data about Formula One car races in 1957 from airgast.com. And so you can just go to the first web page here, and then we'll navigate to the others from that. So this is the general page. This is if you just type in without the .xml or .json or anything. So it's a table of information about races in 1957. And we saw earlier that if you add just .xml to the end of this, it looks exactly the same. That's because this browser is displaying XML properly by default. But if you were to right click on it and go to view page source, you would get this instead. And you can see the structure. This is still XML. And so everything has an opening tag and a closing tag and some extra information in there. But if you type in .json, what you really get is this jumbled mess. Now, that's unfortunate because there is a lot of structure to this. So what I'm going to do is I'm actually going to copy all of this data. And then I'm going to go to a little web page. There's a lot of things you can do here. And it's a cute phrase. It's called JSON Pretty Print. And that is make it look structured so it's easier to read. I just paste that in there. and hit Pretty Print JSON. And now you can see the hierarchical structure of the data. The interesting thing is that the JSON tags only have tags at the beginning. So it says series in quotes and then a colon, and then it gives the piece of information in quotes and a comma, and it moves on to the next one. And this is a lot more similar to the way that data would be represented in something like R or Python. And so it's also more compact. Again, there's things you can do with XML, but this is one of the reasons that JSON is generally becoming preferred as a data carrier for websites. And as you might have guessed, it's really easy to convert between the formats. It's easy to convert between XML, JSON, CSV, etc. And so you can get a web page where you just paste one version in and you get the other version out. There are some differences, but for the vast majority of situations, they're just kind of interchangeable. So, in sum, what do we get from this? Like XML, JSON is semi-structured data, where there are tags that say what the information is, but you can define the tags however you want. And JSON is specifically designed for data interchange. And because it reflects the structure of the data in the programs, that makes it really easy. And then also, because it's relatively compact, JSON is replacing gradually XML on the web as a container for data on web pages. If we're going to talk about coding in data science and the languages that are used, then first and foremost is R. The reason for that is, according to many standards, R is the language of data and data science. For example, take a look at this chart. This is a ranking based on a survey of data mining experts of the software that they use in doing their work. And R is right there at the top. R is first. And in fact, that's important because there's Python, which is usually taken hand in hand with R for data science. But R sees 50% more use than Python does, at least in this particular list. Now, there's a few reasons for that popularity. Number one, R is free and it's open source, both of which make things very easy. Second, R is specially developed for vector operations. That means it's able to go through an entire list of data without having to write for loops to go through it. If you've ever had to write for loops, then you know that that would be kind of disastrous having to do that with data analysis. Next, R has a fabulous community behind it. It's very easy to get help on things with R. You Google it, you're going to end up in a place where you're going to be able to find good examples of what you need. And probably most importantly, R is very capable on its own, but there are 7,000 packages, actually it's many more than that, 7,000 packages that add capabilities to R. Essentially, it can do anything. Now, when you're working with R, you actually have a choice of interfaces. That is, how do you actually do the coding and how do you get your results? R comes with its own IDE or interactive development environment. You can do that, or if you're on a Mac or a Linux, you can actually do R through the terminal, through command line. If you've installed R, you just type R and it starts up. There's also a very popular development environment called RStudio, and that's actually the one that I use and I'll be using for all of my examples. But another new competitor is Jupyter, which is very commonly used for Python. It's what I use for examples there. It works in a browser window, even though it's locally installed. And RStudio and Jupyter, there's pluses and minuses to each one of them. I'll mention them as we get to them. But no matter what interface you use, R's command line, you are typing lines of code in order to get the commands. Some people get really scared about that, but really there's some advantages to that in terms of the replicability and really the accessibility, the transparency of your commands. So for instance, here's a short example of some commands in R. You can enter them into what's called the console, and that's just like one line at a time. That's called an interactive way. Or you can save scripts and run bits and pieces of them selectively. That makes your life a lot easier. No matter how you do it, if you're familiar with programming in other languages, then you're going to find that R is a little weird. It has an idiosyncratic model. It makes sense once you get used to it, but it is a different approach. And so it does take some adaptation if you're accustomed to programming in other languages. Now, once you do your programming and get your output, what you're going to get is graphs in a separate window. You're going to get text and numbers, numerical output in the console. And no matter what you get, you can save the output to files. So that makes it portable. You can do it in other environments. But most importantly, I like to think of this. Here's our box of chocolates where you never know what you're going to get. The beauty of R is in the packages that are available to expand its capabilities. Now, there are two sources of packages for R. One goes by the name of CRAN, and that stands for the Comprehensive R Archive Network. And that's at cran.rstudio.com. And what that does is it takes these 7,000 or so different packages that are available, and it organizes them in topics that they call task views. And for each one, if they've done their homework, you have data sets that come along with that package. You have a manual in PDF format, and you can even have vignettes where they run through examples of how to do it. Another interface is called Crantastic, and the exclamation point is part of the title. That's at crantastic.org. And what this is an alternative interface that links to CRAN. So if you find something like in Crantastic and you click on the link, it's going to open in CRAN. But the nice thing about Crantastic is it shows the popularity of packages, and it also shows how recently they were updated. And that can be a nice way of knowing that you're getting sort of the latest and greatest. Now, from this very abstract presentation, we can say a few things about R. Number one, according to many, R is the language of data science. And it's a command line interface. You're typing lines of code. So that gives it both a strength and it's a challenge for some people. But the beautiful thing is the thousands and thousands of packages of additional code and capability that are available for R that make it possible to do nearly anything in this statistical programming language. When talking about coding in data science in the languages, along with R, we need to talk about Python. Now, Python, the snakes, is a general purpose program that can do it all, and that's its beauty. If we go back to this survey of the software used by data mining experts, you see that Python's there. It's number 3 on the list. And what's significant about that is on this list, Python is the only general purpose programming language. It's the only one that can theoretically be used to develop any kind of application that you want. That gives it some special power compared to all these others, most of which are very specific to data science work. So the nice things about Python are, number one, it's general purpose. It's also really easy to use. And if you have a Macintosh or a Linux computer, Python is built into it. Also, Python has a fabulous community around it with hundreds of thousands of people involved. And also, Python has thousands of packages. Now, it actually has something like 70 or 80,000 packages, but in terms of ones that are specific to data, there are still thousands available that give it some incredible capabilities. Now, a couple of things to know about Python. First is about versions. There are 2 versions of Python that are in wide circulation. There's 2.x, so that means like 2.5, 2.6, and there's 3.x, 3.1, 3.2. Version 2 and version 3 are similar, but they're not identical. And in fact, the problem is this. There are some compatibility issues where code that runs in one does not run in the other. And consequently, most people have to choose between one or the other. And what this leads to is that many people still use 2.x. I have to admit, the examples that I use, I'm using 2.x because so many of the data science packages are developed with that in mind. Now, let me say a few things about interfaces for Python. First, Python does come with its own interactive development and learning environment. They call it idle. You can also run it from the terminal or command line interface or any IDE that you have. Now, a very common and very good choice is Jupyter. Jupyter is a browser-based framework for programming, and it was originally called IPython, and that served as its initial version. So a lot of times when people talk about IPython, what they're really talking about is Python in Jupyter, and the two are sometimes used interchangeably. One of the neat things you can do is there are 2 companies, there's Continuum and Enthought, both of which have made special distributions of Python with hundreds and hundreds of packages pre-configured to make it very easy to work with data. I personally prefer Continuum Anaconda. It's the one that I use. A lot of other people use it, but either one's going to work and it's going to get you up and running. And like I said with R, no matter what interface you use, all of them are command line. You're typing lines of code. Again, there are some tremendous strengths to that, but it can be intimidating to some people at first. In terms of the actual commands of Python, you have some examples here on the side. The important thing to remember is that it's a text interface. On the other hand, Python is familiar to millions of coders because it's very often a first programming language that people learn to do general purpose programming. And there are a lot of very simple adaptations for data that make it very powerful for data science work. So let me say something else again. Data science loves Jupyter, and Jupyter is the browser-based framework. It's a local installation, but you access it through a web browser that makes it possible to really do some excellent work in data science. There's a few reasons for this. When you're working in Jupyter, you get text output, and you can use what's called Markdown as a way of formatting documents. You can get inline graphics where the graphics just show up directly beneath the code that you did it. Also, it's really easy to organize and present and to share analyses that are done in Jupyter, which makes it a strong contender for your choices in how you do data science programming. Another one of the beautiful things about Python, like R, is that there are thousands of packages available. In Python, there's one main repository. It goes by the name PyPy, which is for the Python Package Index. Right here, it says there's over 80,000 packages, and 7,000 or 8,000 of those are for data-specific purposes. Now, some of the packages that you'll get to be very familiar with are NumPy and SciPy, which are for scientific computing in general. Matplotlib and a development of it called Seaborn are for data visualization and graphics. Pandas is the main package for doing statistical analysis. And for machine learning, almost nothing beats scikit-learn. And when I go through hands-on examples in Python, I will be using all of these as a way of demonstrating the power of the program for working with data. So, in sum, we can say a few things. Number one, Python is a very popular program, familiar to millions of people, and that makes it a good choice. Second, of all the languages we use for data science on a frequent basis, this is the only one that's general purpose, which means it can be used for a lot of things other than processing data. And it gets its power, like R does, from having thousands of contributed packages, which greatly expand its capabilities, especially in terms of doing data science work. A choice for coding in data science, one of the languages that may not come immediately to mind when they think data science, is SQL or SQL. And SQL is the language of databases. And we think, why do we want to work in SQL? Well, to paraphrase the famous bank robber Willie Sutton, who apparently explained why he robbed banks and said, because that's where the money is. The reason we would work with SQL in data science is because that's where the data is. And so let's take another look at our ranking of software among data mining professionals. And there's SQL. It's third on the list. And also of this list, it's the first database tool. Other tools in there, for instance, get much fancier and they're much newer and shinier, but SQL's been around for a while and is very, very capable. Now there's a few things to know about SQL. By the way, you'll notice I'm saying SQL, even though that stands for something. It stands for Structured Query Language. SQL is a language. It's not an application. There's not a program SQL. It's a language that can be used in different applications. Primarily, SQL is designed for what are called relational databases. And those are special ways of storing structured data that you can pull in, you can put things together, you can join them in special ways, you can get some summary statistics. And then what you usually do is you then export that data into your analytical application of choice. So the big word here is RDBMS, and that stands for Relational Database Management System. And that's where you will usually see SQL as a query language being used. In terms of relational database management systems, there are a few very common choices. In the industrial world where people have some money to spend, there's Oracle database is a very common one, and Microsoft SQL or SQL Server. In the open source world, two very common choices are MySQL. Even though we generally say SQL, when it's here, you generally say MySQL. And then another one is PostgreSQL. These are both open source free versions of the language. They're sort of dialects of each that make it possible for you to be working with databases and get your data out. The neat thing about them, no matter what you do, is that databases minimize data redundancy by using connected tables. Each table has rows and columns, and they store different levels or different of abstraction or measurement, which mean you only have to put the information in one place and then it can refer to lots of other tables. Makes it very easy to keep things organized and up to date. When you're looking at a way of working with a relational database management system, you get to choose in part between using a graphical user interface or GUI, and some of those include SQL Developer and SQL Server Management Studio, two very common choices. And there are a lot of other ones like Toad and some other choices that are graphical interfaces for working with these databases. And there are also text-based interfaces. So really any command line interface and any interactive development environment or programming tool is going to be able to do that. Now you can think of yourself being on the command deck of your ship and learn a few basic commands that are very important for working with SQL. There are just a handful of commands that can get you most of where you need to go. There is the select command where you're choosing the cases that you want to include. From says which tables are you going to be extracting them from. Where is a way of specifying conditions, and then order by, obviously, is just a way of putting it all together. This works because usually when you're in a SQL database, you're just pulling out the information. You want to select it, you want to organize it, and then what you're going to do is you're going to send the data to your program of choice for further analysis, like R or Python or whatever. So in sum, here's what we can say about SQL. Number one, as a language, it's generally associated with relational databases, which are very efficient and well-structured ways of storing data. Just a handful of basic commands can be extremely useful when working with databases. You don't have to be a super ninja expert. Really, a handful, 5, 10 commands will probably get you everything you need out of a SQL database. And then once you get the data organized, it's typically exported to some other program for analysis. When you talk about coding in any field, one of the languages or one of the groups of languages that come up most often are C, C++, and Java. Now, these are extremely powerful applications and very frequently used for sort of professional production level coding. In data science, the place where you're going to see these languages most often is in the bedrock, the absolute fundamental layer that makes the rest of data science possible. So for instance, C and C++. C is from the 60s, C++ is from the 80s, and they have extraordinarily wide usage. And their major advantage is that they're really, really fast. In fact, C is usually used as the benchmark for how fast is a language. They're also very, very stable, which makes them really well suited to production level code and, for instance, server use. What's really neat is that in certain situations, if time is really important, if speed's important, then you can actually use C code in R or other statistical languages. Next is Java. Java is based on C++. Its major contribution was the WARA, or write once, run anywhere. The idea that you're going to be able to develop code that is portable to different machines and different environments. And because of that, Java is actually the most popular computer programming language overall against all tech situations. And the place where you would use these in data science is, like I said, when time is of the essence, when something has to be fast, it has to get the job accomplished quickly, and it has to not break, then these are the ones that you're probably going to use. The people who are going to use it are primarily going to be engineers. So the engineers and the developers, the software developers who deal with the inner workings of the algorithms in data science, or the back end of data science, the servers and the mainframes and the entire structure that makes analysis possible. In terms of analysts, people who are actually analyzing the data typically don't do hands-on work with the foundational elements. They don't usually touch C or C++. More the work is on the front end or closer to the high-level languages like R or Python. In sum, C, C++, and Java form a foundational bedrock and the back end of data and data science. And they do this because they're very fast and they are very reliable. On the other hand, given their nature, that work is typically reserved for the engineers who are working with the equipment that runs in the back that makes the rest of the analysis possible. I want to finish our extremely brief discussion of coding and data sciences and the languages that can be used by mentioning one other that's called Bash. And Bash really is a great example of old tools that have survived and are still being used actively and productively with new data. You can think of it this way. It's almost like typing on your typewriter. You're working at the command line. You're typing out code through a command line interface, or CLI. Now, this method of interacting with computers practically goes back to the typewriter phase because it predates monitors. So before you even had a monitor, you would type in the code and it would print it out on a piece of paper. And the important thing to know about the command line is it's simply a method of interacting. It's not a language because lots of different languages can run at the command line. So for instance, it's important to talk about the concept of a shell. Now in computer science, a shell is a language or something that wraps around the computer. It's a shell around the language that is the interaction level for the user to get things done at the lower levels that aren't really human friendly. On Mac computers and Linux, the most common is Bash, which is short for Born Again Shell. On Windows computers, the most common version is PowerShell. But whatever you do, there actually are a lot of choices. There's the Bourne shell, there's the C shell, which is why I have a C shell right here. The Z shell, there's Fish for friendly interactive shell, and a whole bunch of other choices. But Bash is the most common on Mac and Linux, and PowerShell is the most common on Windows as a method of interacting with the computer at the command line level. Now there's a few things you need to know about this. First, you have a prompt of some kind. In Bash, it's a $sign, and that just means type your command here. Then the other thing is you type one line at a time. It's actually amazing how much you can get done with what's called a one-liner program by sort of piping things together so one feeds into the other. You can run more complex commands if you use a script. And so you call a text document that has a bunch of things in it, and you can get much more elaborate analyses done. Now we have our tools here. In Bash, we talk about utilities. And what these are specific programs that accomplish specific tools. Bash really thrives on do one thing and do it very well. There are two general categories of utilities for Bash. Number one is the built-ins. These are the ones that come installed with it, and so you're able to use them at any time by simply calling in their name. Some of the most common ones are cat, which is for catenate, and that's to put information together. There's awk, which is its own interpreted programming language, but it's often used for text processing from the command line. By the way, the name awk comes from the initials of the people who created it. Then there's grep, which is for global search with a regular expression, and print. It's a way of searching for information. And then there's sed, which stands for stream editor. And its main use is to transform text. You can do an enormous amount with just these four utilities. A few more are head and tail that display the first or last 10 lines of a document. Sort and unique, which sort and count the number of unique answers in a document. WC, which is for word count. And printf, which formats the output that you get in your console. And while you can get a huge amount of work done with just this small number of built-in utilities, there are also a wide range of installables or other command line utilities that you can add to Bash or to whatever program you're using. So for instance, some really good ones that have been recently developed are JQ, which is for pulling in JSON or JavaScript object notation data from the web. And then there's JSON to CSV, which is a way of converting JSON to CSV format, which is what a lot of statistical programs are going to be happier with. There's Rio, which allows you to run a wide range of commands from the statistical programming language R in the command line as part of Bash. And then there's Big MLer. And this is a command line tool that allows you to access Big ML's machine learning servers through the command line. Normally you do it through a web browser and it accesses their servers remote. It's an amazingly useful program, but to be able to just pull it up when you're in the command line is an enormous benefit. What's interesting is that even though you have all these opportunities, all these different utilities, you can do amazing things, and that there still is active development of utilities for the command line. So let's say this, in sum, despite being in one sense as old as the dinosaurs, the command line survives because it is extremely well evolved and well suited to its purpose of working with data. The utilities, both the built-in and the installables, are fast and they are easy. And generally they do one thing and they do it very, very well. And then surprisingly, there is an enormous amount of very active development of command line utilities for these purposes, especially with data science. One critical task when you're coding in data science is to be able to find the things that you're looking for. And regex, which is short for regular expressions, is a wonderful way to do that. You can think of it as the supercharged method for finding needles in haystacks. Now, regex tends to look a little cryptic. So for instance, here's an example of something that's designed to determine whether something is a valid email address. And it specifies what can go in the beginning. You have the @ sign in the middle. Then you've got a certain number of numbers and letters, and then you have to have a dot something at the end. And so this is a special kind of code for indicating what can go where. Now, regular expressions, or regex, are really a form of pattern matching in text. And it's a way of specifying exactly what needs to be where, what can vary, and how much it can vary. And you can write both specific patterns, say I only want a one-letter variation here, or very general, like the email validator that I showed you. And the idea here is you can write this search pattern, your little wildcard thing. You can find the data, and then once you identify those cases, then you can export them into another program for analysis. So here's a short example of how it can work. What I've done is I've taken some text documents. They're actually the text to Emma and to Pygmalion, 2 books I got off of Project Gutenberg. And this is the command, grep::l.ve space *.txt. So what I'm looking for are lines in either of these books that start with L. Then they have one character, can be whatever, and then that's followed by VE. And then the .txt means search for all of the text files in that particular folder. And what it found is lines that began with love and lived and lovely and so on. Now, in terms of the actual nuts and bolts of regular expressions, there are some certain elements. There are literals, and those are things that mean exactly what they are. You type the letter L, you're looking for the letter L. There are also meta characters, which specify, for instance, things needs to go here. They're characters, but they actually really code that give representations. There are also escape sequences, which are something that you use to say, well, normally this character is used as a variable, but I actually want to really look for a period as opposed to a placeholder. Then you have the entire search expression that you create, and then you have the target string, the thing that it's searching through. So let me give a few very short examples. This is the caret. It's the sometimes called a hat, or in French, a circonflexe. And what that means is you're looking for something that's at the beginning of the text that you're searching. So for example, you can have caret and capital M. That means you need something that begins with a capital M. So for instance, the word Mac, true, it will find that. But if you have iMac, there's a capital M, but it's not the first thing. So that'll be false. It won't find that. The $sign means you're looking for something that is at the end of the string. So for example, ing and then $sign, that'll find the word fling because it ends with ing, but it won't find the word flings because it actually ends with an S. And then the dot, the period, simply means we're looking for one letter, and it can be anything. So for example, you can write AT period, and that will find data because it has an A, a T, and then one letter after it. But it won't find flat because flat doesn't have anything after the AT. And so these are extremely simple examples of how it can work. obviously it gets more complicated, and the real power is when you start combining these bits and elements. Now, one interesting thing about this is you can actually treat this as a game. I love this website. It's called regex golf, and it's at regex.alf.nu. And what it does is it brings up lists of words, 2 columns, and your job is to write a regular expression in the top that matches all the words on the left column and none of the words on the right, and that uses the fewest characters possible. And you get a score. And it's a great way of learning how to do regular expressions and learning how to search in a way that's going to get you the data that you need for your projects. So, in sum, regex or regular expressions help you find the right data for your project. They're very powerful and they're very flexible. Now, on the other hand, they are cryptic, at least when you first look at them, but at the same time, it's like a puzzle, and it can be a lot of fun if you practice it and you see how you can find what you need. I want to thank you for joining me in coding and data science, and we'll wrap up this course by talking about some of the specific next steps that you can take for working in data science. The idea here is that you want to get some tools and you want to start working with those tools. Now, please keep in mind something that I've said at another time. Data tools and data science are related, they're important, but don't make the mistake of thinking that if you know the tools that you have done the same thing as actually conducted data science. That's not true. People sometimes get a little enthusiastic and they get a little carried away. What you need to remember is the relationship really is this. Data tools are an important part of data science, but data science itself is much bigger than just the tools. Now, speaking of tools, remember there's a few kinds that you can use and that you might want to get some experience with these. Number one, in terms of apps or just specific built applications, Excel and Tableau are really fundamental for both getting the data from clients or doing some basic data browsing. And Tableau is really wonderful for interactive data visualization. I strongly recommend that you get very comfortable with both of those. In terms of code, it's a good idea to learn either R or Python, or ideally to learn both because you can use them hand in hand. In terms of utilities, it's a great idea to learn how to work with Bash, the command line utility, and to use regular expressions or regex. You can actually use those in lots and lots of programs, regular expressions. And so they can have a very wide application. And then finally, data science requires some kind of domain expertise. You're going to need some sort of field experience or intimate understanding of a particular domain and the challenges that come up and what constitutes workable answers and the kind of data that's available. Now, as you go through all of this, you don't need to build this monstrous list of things. Remember, you don't need everything. You don't need every tool. You don't need every function. You don't need every approach. Instead, remember, get what's best for your needs and for your style. But no matter what you do, remember, tools are tools. They're a means to an end. Instead, you want to focus on the goal of your data science project, whatever it is. And I can tell you really, the goal is meaning, extracting meaning out of your data to make informed choices. In fact, I'll say a little more. The goal is always meaning. And so with that, I strongly encourage you, get some tools, get started in data science, and start finding meaning in the data that's around you.